Hello everyone. I'm Gevorg from Podcastle, where my team and I working on different AI projects in audio domain. Today I present one of them, how to build and scale text-to-speech systems. Let's start by definition. What is text-to-speech? To generate intelligible natural speech from text. Here I want to pay attention special terms, intelligible and natural, that I used in definition, where intelligible means that generated output should be easy comprehensible, and naturalness, that synthesized output we want to be close real speech as much as possible. Enabling machines to speak is an important part of AI, and text-to-speech has long research history, starting from 1950s till nowadays, and we can separate different research phases where early stage text-to-speech systems, such as format synthesis, they generate highly intelligible speech, but they are not natural. There is one turning point happened in 2016 after WaveNet release, where they showed that this system, in terms of naturalness, outperforms previous text-to-speech systems. And after WaveNet release, deep neural speech synthesis era begins. Building text-to-speech system has several challenges. First challenge comes from data collection. In typical neural systems, it requires high-quality data, where high quality means it should contain precise pronunciation, accurate transcription, speaker should follow punctuations, it should read in consistent way, otherwise generated speech from sentence to sentence will vary undesirably. When it comes to large-scale setup, diversity in volume matters, which means your dataset should contain tens of thousands speakers covering with different languages, styles, accents, emotions, or it should contain audio from different domains like podcasts, audiobook, conversational speech, and so on. Second challenge comes from generative nature of task. Same speaker, same sentence can read various multiple ways, which is known one-to-many mapping issue, and advanced generative approach requires to handle those pronunciation and intonation nuances. Another challenge comes from audio quality and naturalness. Naturalness, the primary goal that neural text-to-speech systems aim to achieve human-level quality. And the audio quality, we want to reduce artifacts such as vibration issues, robotic tone of speech, or any kind of audible artifact. Reducing adds another complexity to the task. And last point that I want to mention here is controllability, where advanced systems should allow a set of predefined voices to generate speech. It should easily adapt on custom voices, and there are scenarios where you just give a couple of seconds of recordings as a prompt. It should capture all the nuances from that short period of audio recording and generate personalized speech. And there are also approaches that give control over emotions, styles, accents. How Podcastle uses text-to-speech? We have three main use cases. First use case is predefined voice library, where we have high-quality voices differing from age, gender, emotions, and it simplifies content creation for our users. And second feature is voice cloning, where users provide a set of recordings. We adapt our base model to match these recordings nuances, and they can generate a speech by their own voice. Already thousands of speakers already clone their voice, leveraging our product. And the last feature, podcast editing, which is not released yet, but MVP model is ready, and we will release this soon. It allows add, remove, replace text snippets in podcasts. And basically, it means they can seamlessly integrate new speech with existing audio content. And how typical NeoTTS pipeline works? The most common one consists of three main building blocks: text analysis, synthesizer network, and vocoder network. Where text analysis takes raw text, which contains lots of ambiguities, and transform it linguistic features, such as phonemes, which are one-to-one pronunciation mapping. Basically, text analysis job is to simplify synthesizer work. And synthesizer takes these linguistic features and transforms into acoustic features, the male spectrogram, which is commonly spread in research works. And I want to highlight here that synthesizers do a primary job. It learns alignments from text to audio, all prosodic nuances, naturalness comes from modeled by synthesizer. And the last point, we give these acoustic features to the vocoder, which transform audio signal into waveform domain. And there are tons of research studies that tries to improve certain aspects of this typical NeoTTS pipeline. Right side diagram illustrates those model connection and the evaluation of NeoTTS pipeline before LLM era. About Podcastle speech collection pipeline, we currently collect over 500,000 of hours raw data with over hundreds of thousands hours cleaned and processed, which we use in our text-to-speech experiments. Our collection pipeline include different sources, such as podcast, audiobook. Even we are using our internal data for our text-to-speech systems, and we have simplified pipeline where we split raw data into the chunks, and we trained set of classifiers that are accept or rejects this chunk in context of TTS task. And last step, we transcribe them leveraging open source ASR systems. One of the key foundations to build large-scale text-to-speech systems are speech tokenizers. And in this presentation, I include several high-performing speech tokenizers, such as encoding from Meta Research, Descript Audio Encoding, and Factorize Codec from Microsoft, which are extensively used to build text-to-speech large-scale models. Scaling up. Transitioning from conventional NeoTTS to large-scale models, if someone tries to just increase number of parameters and scale of data, it will not work. Advancement in generative modeling, such as large language models or diffusion models, they showed that if we scale their data size and number of parameters, the performance increases. We want to leverage them. In traditional NeoTTS system, where we can see that intermediate representation is mel spectrogram, in large-scale models case, if we want to model this part leveraging conditional LLMs, in this case, we will use speech tokens. In diffusion model case, we will see lots of that researchers using mel spectrogram. And in terms of training data scale, if a conventional NeoTTS system requires a couple of hundreds hours to build such systems. Large-scale setup, it requires tens of thousands hours. It can scale up to million hours to build well generalizable large-scale TTS model. VoiceBox. VoiceBox is from Meta Research, one of the most influential work in public research, and it leverages so-called diffusion models, more precisely conditional flow matching, which has close relationship with diffusion models, but it's more faster to train, more stable to train, and later you could do just dozens of flow steps, and it matches quality doing it hundreds of diffusion steps. And leveraging this conditional flow matching paradigm, VoiceBox is trained, and it consists of two models, duration model and audio model, where duration model takes phonemes and predicts each phoneme duration. After that, we upsample too much audio length, and we condition it to audio model with masked audio context, and this masked part, audio model job is to infill this masked part. And the authors showed that if we scale these systems, a couple of hundreds of million parameters and 50,000 of hours data, it shows emergent abilities. What it means, we can use it different applications such as speech editing, transient noise removal, zero-shot TTS. I want to highlight this one especially. You just provide a couple of seconds audio prompt, and it can capture all the nuances from this prompt and generate personalized speech. And the last bonus is like text-only sampling. We just give text without audio context, and it can generate diverse audio samples with different voices, different styles. However, one limitation this voice box system comes from its duration predictor, which limits variability of audio model. The authors use two approaches, non-autoregressive, which is not generative. They train it leveraging regression laws, and they also tried same conditional flow matching training paradigm to train duration predictor, but it's not stable. We also try, and our findings are matched with their insights. And we try another approach. We formulate duration predictor as an autoregressive one, and we condition phonemes and previous duration, and autoregressive decoder-only transformer job is to predict, based on these conditions, next duration. And after doing a couple of changes on output side and objective side, we were able to stabilize and make it generative. And compared to non-autoregressive counterpart, it generates more variable output, which is also visible from metrics. So the autoregressive duration predictor generates variable output, but still there is room for improvement in terms of naturalness, in terms of variability. And we want to completely get rid of this duration predictor because it requires to train external aligners, which is not easy to scale new languages, and it's hard to train. And we completely get rid of duration predictor in this Castle flow system, where we have trained our own speech tokenizer, which is single codebook approach, and we want disentangle speaker characteristics from the tokens, and our tokens mainly are responsible content information. And the second network, which we call flow decoder, takes these content-wise speech tokens and audio masked context, and flow decoder reconstructs in fields full spectrogram. And the main responsibility to inject speaker and acoustic information from the prompt into the remaining content-wise speech tokens. And the last part, we call this speech token predictor, which is autoregressive decoder-only network, which takes the phonemes and previous speech tokens and main responsibility to predict next token. And the good thing is that later we could use advanced sampling techniques coming from the LLMs. In this results slide, I include a couple of objective metrics such as word error rate and speaker similarity one. And our current results are comparable with strong baselines. And in some cases, we also outperform, like in this autoregressive case, first classic work volley has much higher word error rate than our Castle flow system. And in this slide, I include a couple of demonstration examples to highlight where are we in terms of naturalness and quality.
Revlon, love is on, a brand that stands for glamour, romance, and passion.
And this is just a prompt that we give the text-to-speech system. And this is the synthesized output.
Yawn, Robert said, stretching out on the park bench. This sunshine makes me sleepy.
We can see that all the voice timbre styles captured by the model.
Her face was against his breast.
So this prompt contains anger emotion.
What? You're telling me you've never seen a single episode of Game of Thrones before?
And it also captures emotions.
I'm not surprised that won 8 consecutive awards in customer service. A proud smile spread across his face as he softly said, "Son, your accomplishments fill my heart with such joy and pride."
It also can handle accents.
30 days is just about the right amount of time to add a new habit or subtract a habit. He relayed his conversation with the bartender, saying, "I told him, your signature cocktail is simply a margarita with a fancy garnish."
And it also can capture acoustic environment since we give enrolled way acoustic prompt. And yeah.
Once upon a time, a white snake and a green snake living in a remote mountain became immortal and obtained superpowers after centuries of practice.
This result is second model, castle flow, and we can see that this is more natural and pause is handled way compared to the previous one.
I was talking to my friend and she's all excited about her trip to Europe, and I'm just like so jealous, right?
And it can also handle conversational speech, which contains lots of disfluencies. Thank you for your attention.
Thank you. Can you go back to the results slide?
Yeah.
One. So ground truth, that means ground truth. So you have text and speech, and then you use whisper to get to text again, and then from there you use text. So what does ground truth mean here?
Ground truth means that since we use ASR system and it includes odds errors, we also report here ground truth original recordings ASR performance as well.
Original recording, but this original recording had different text, right?
We use original text from the recordings to generate speech.
Video recordings.
Yeah.
I see.
For computation of metrics.
I see. So these three things below are your systems?
Yes.
Flow is?
I include here autoregressive version and VoiceBox, VoiceBox results. And these last three rows are our results. And this Castle VB non-autoregressive one has close similarities with VoiceBox. There are a couple of differences, like we use our internal aligner, our internal phonemizer, and we can see that there is a slight difference in terms of order rate and speaker similarity metrics. This slight decrease in speaker similarity, we believe it comes from the scale of training. Original authors used 32 GPUs. We just use single AMD GPU.
I see. And some of these things are open, right? This VoiceBox.
VoiceBox is not open. It has sensitivity issues, and if ASR system, they can easily publish their weights, but large-scale text-to-speech systems, they can't.
Looks like only they publish with predefined voices, right? If they want to support you to put on the voice, then it's...
In typical Neuro TTS pipeline, which are not trained in a large-scale fashion, you can find good works in open source research, but when it comes to large-scale setup, I haven't seen any influential works that put from the giants.
I see. So that's why you develop binary and so on to understand the motivation why you want to develop these things from scratch. Of course. Do we have more questions?
Yeah, thank you for the presentation. It was very good to see. I have a question about Podcastle 2, which you mentioned. It sounds really scary. Is it possible to detect it was generated with LLM or not? Or it was edited with LLM or not?
When it comes to couple of words, our current results we can't indistinguish, but when it comes to large chunk of snippets, human can detect, but our goal is to even create systems that in a long chunks will not easily detectable.
Detectable like human, but maybe some.
Human.
Okay, we're right on time. Thank you very much again. We have a short lunch break, the last one, and then we'll get back to see more speakers.
Thank you.